Welcome. Today we discuss a proof of the division algorithm for polynomials. And before we dive into that proof, I wanted to make an interesting side note here that today is actually Christmas Day of 2012, December the 25th, 2012, and wanted to give you something to think about on the subject of division, that as Jesus came into the world, he, in fact, and he alone, divided all of human history into two parts. We refer to these as the BC era or the AD era. And isn't it interesting that even non-Christians the whole world over pay homage to this very event that happened in the history of mankind? Something to think about on the theme of division. All right, so coming now to the subject at hand, I have here some preliminaries before we look at the theorem itself. The preliminaries are that with the uppercase or the capital letters, the P, D, Q, and R, I'm going to use these symbols to refer to polynomials. And I'm going to use the lowercase symbols, little p, d, q, and r, to be, respectively, each of those polynomials' degrees. Now, the capital P polynomial is referred to as the dividend polynomial. The capital D is the divisor. Cap Q is the quotient, and cap R is the remainder. You might be more familiar with the way that we were taught how to divide back in grade school. We always did it in the form, for example, 3 divides 4. We would say 3 divides 4 one time, okay, such that you would have this, and then we would have a remainder of 1, okay. So here, the 3 is your divisor. This is your dividend. This 1 would then be the quotient. And of course, that 1 is the remainder. So effectively, in that notation, what we're talking about is the following. We're talking about this. Okay. Very good. So, now let's read the division algorithm for polynomials. It states that for a polynomial P having a divisor D different from 0, of course, this divisor has to be different from 0 for the very simple reason that division by 0 is undefined, right? So for a polynomial P having divisor D different from 0, there exist unique polynomials Q and R such that this happens, and this is exactly what we showed here, okay, just written out in algebraic form, all right, where you have one of two possibilities, that in case 1, when the degree of the divisor, little d, is 0, then the remainder is 0, or else, in case 2, when the degree of the divisor is larger than or equal to 1, the degree of your remainder is strictly less than the degree of your divisor. Okay? Now, to get at a proof of this theorem, we're going to look at two key terms here in the statement of the theorem itself. Namely, that there exists, so in the first case, this there exists is about existence, okay? And it's not just about existence, but that it's also about uniqueness. So these are the two terms that we need to pay attention to and also treat in our proof. I didn't mention up here that there are other constants apart from the degrees of the polynomial divisor, quotient, or the remainder, that we will make use of some of these symbols, like, for example, a sub I or b sub I, c, k, n. All of those are constants, okay? So let's begin with the first part. Let's look at first, let's try and treat existence. All right, so for existence, here is my proof. I can say that for existence, I'm going to try and show existence using an approach, a popular approach in proofs, in mathematical proofs, known as the principle of mathematical induction. So let's use the principle Okay, so I can, sometimes we can just refer to this as PMI. The principle of mathematical induction has two parts, as you probably know. One part is your basis step. And the second part is your inductive step. All right. Now, in the basis step, I'm going to just take the degree of the polynomial little p to be 0. And the way to distinguish between little p and capital P, in the way I'm going to draw this or write this out, when I refer to capital P, I'll try and say it's p as a function of x. And when I'm talking about little p, there won't be that function of x. So hopefully from the context and also that little device that I just mentioned there, between those two it should be clear what we're talking about. In the inductive step, we're going to assume that the case of the theorem holds for the degree of the polynomial equal to some value k, and then we will try and prove the k plus first step, okay? All right, let's look at each of these, and let me also remind us one more time that in each of these we've got two cases to treat, okay? So let's look at the very first part. So as the basis step, I'm going to show at the level where the degree of the polynomial is 0, p is 0, then it should be obvious that when the degree of the polynomial is 0, the polynomial itself has to be a constant, okay? So let me just call that polynomial, capital P, some constant, and we'll just use the letter C for the constant for now, okay? Like I mentioned just a moment ago, we have two cases to treat here. We have case 1 and case 2. So let's look at case 1. Case 1, i.e., where the degree of the polynomial is 0. Okay? The degree of the divisor polynomial, I should say, is 0. Now, since d is 0, by the same rationale that we just used up there, you should be able to say that the divisor polynomial is some constant too. Let me call it a constant little b. And since, by definition, the divisor polynomial must be different than 0, okay, that's just by definition. Division by 0 is not allowed. It's undefined. Okay? Since the divisor polynomial is different from 0, all of this implies then that b, the constant, must be different than 0. And so, therefore, since b is different than 0, you can write very easily, we're trying to show the existence of a q and an r, I can write my q very easily as c over b, and my r very simply as 0. And when I do that, therefore, I get the following. I get that b times c over b plus 0, the b's cancel, is all equal to c, such that, notice that this right here is my divisor polynomial. This right here is my quotient. This is the remainder. And of course, this is the dividend polynomial. And so, in this first case, we have in fact shown this in case 1, where the degree of the divisor polynomial is 0. Let's look at case 2. Case 2, i.e., the degree of the divisor polynomial is greater than or equal to 1. Okay, again, we're trying to show existence here of a q and an r. I can just write very simply that q is 0, and let me make the remainder some constant value, c. Okay, and if you do that, look at what we have. We get that thus, by doing this, I get d of x times 0 plus c is equal to c. So once again, we have d of x, q of x, r of x, and p of x, and we have shown therefore that our polynomial is just a constant value. And it's also important here to note that since the remainder polynomial is a constant c, this implies that the degree of my remainder has to be 0. And if the degree of my remainder is 0, this implies then that since we said that this is the case where the degree of the divisor polynomial is greater than or equal to 1, that in fact r is strictly less than d. Okay? So that completes, in the existence portion for my basis step, that completes a proof for that step. Now we're going to go to a higher level, and let me go to a new page here. Very good. So here in the higher step, we are at a inductive step, right? We're still at the existence, Let me try that again. We're still at the stage of existence. Where we're doing this right here, but I'm at the inductive step now. And at the inductive step, I'm going to say, throughout this step, we're going to assume that for some p equal to k, all right, there exists a q tilde and an r tilde. Let me, just as I said earlier, let me write these in terms of x so there's no confusion what we're talking about here. We are in fact talking about the quotient polynomial and the remainder polynomial at the kth step. We assume that there exist these q and r tilde such that I can write my polynomial, the dividend polynomial, p tilde, in this fashion. Okay. All right. We assume that we need now sometimes I will abbreviate need to show as capital NTS. We need to show that there exists a q and an r polynomial for the k plus 1 case such that, of course, the theorem, the statement of the theorem which is written here holds, meaning that I can write this in this fashion. Okay, so let's go ahead and try that out. So in this case, again, we've got two cases. I've got case 1 and I've got case 2. So let's look at each of them one by one. So case 1. In case 1, i.e., the degree of the divisor polynomial is 0. Okay? And in a sense, this is like a trivial case, since the degree of the divisor polynomial is 0. Once again, my divisor polynomial is some constant. Let me call it b. And as we did up above, the b must be different than 0, since d is by definition different than 0. Okay? Now, therefore, since b is different than 0, we write the quotient polynomial as just the polynomial of interest divided by b. Since b is 0, I can do that. And I will go ahead and set the remainder polynomial as being 0. Thus, I get that b times p of x divided by b plus 0 is equal to p of x. Again, this right here is our divisor, our quotient that we were trying to show exists, our remainder that we were trying to show exists, and of course this is the dividend polynomial. So that was simple enough. Let's go on to case 2. in case 2, the degree of the divisor polynomial is greater than or equal to 1. Okay? Let's see how we can do this one. By the inductive step, we have a Q tilde polynomial and an R tilde polynomial such that P tilde polynomial is equal to D times Q tilde plus R tilde. Okay? And we must show that P of X holds at K plus 1 case where R is strictly less than D. That means that the degree of the remainder polynomial is strictly less than the degree of the divisor polynomial. Okay. Let's first note the form of this polynomial at the K plus 1 step. Okay? The K plus 1 case polynomial P of X I can write as being of the form A sub K plus 1 times X to the K plus 1 power plus A sub K times X to the kth power plus dot 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 A sub 1 to the X to the first power plus A sub 0, such that if this is really at the K plus 1 polynomial level, the coefficient here, A sub K plus 1, must be different than 0. Otherwise, it would not be a K plus 1 degree polynomial, right? So the coefficient A sub K plus 1 must be different from 0. And likewise, my divisor polynomial, I could say, is of the form B sub D X to the dth power plus B sub D minus 1 X to the D minus 1 power plus dot 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 plus B sub 1 X to the first power plus B 0, where such that the B sub D coefficient has to also be different from 0. Okay? Otherwise, it wouldn't be a polynomial of the dth degree, where we're saying it's some D larger than or equal to 1. And because of this fact, and because of this fact, okay, because of these two facts, therefore, the quotient or the ratio of the A sub K plus first coefficient term and the B sub D coefficient term, that ratio, that quotient has to be different from 0, since both are non-zero. And we now look at our inductive step. Okay, from our inductive step, we have our polynomial at the p equal to kth level, which we had assumed, can be written as the following. I could say it's p tilde x equal to the p of x, which I'm interested in, minus, now the p of x, let's remember, the p of x had this form, right? But the p tilde is the polynomial knocked down by 1 degree. So I could take out this first term, which would be saying minus the a sub k plus 1 x to the k plus 1, if I subtract that. But now look how interesting this is. But the a sub k plus 1 x to the k plus 1 power, that term is equal to a k plus 1 times x to the k plus 1 minus d times x to the dth power. Okay, remember that when you're multiplying these two terms, this term with that term, you're adding the exponents there. And so this x to the k plus 1 minus d times x to the d becomes x to the k plus 1 minus d plus d. The minus d and plus d cancel, and you're left with x to the k plus 1 term. So I haven't really done anything so drastically different there. It's the same. They are equal. But that allows me to write this as follows. A sub k plus 1 times x to the k plus 1 minus d. Now this x to the dth power, remember, is times the divisor polynomial divided by the b sub d term. Let's just take a quick peek at that one, right? It's right up here. If I divide both sides of this expression by the non-zero b sub d term, then in fact I'm going to get my x sub x raised to the dth power term right over there. Okay, so having done that, therefore, now let's put it all together, okay? So therefore, I could say that my p tilde polynomial is equal to the px minus, okay, the a k plus 1, sorry, a k plus 1 term divided by the b sub dth term, which is this guy right here. Okay, I'm bringing that outside, times x to the k plus 1 minus d times the dx, the divisor polynomial. But what was the p tilde polynomial? This guy right here is equal to, let's just remember what that was. That was the kth inductive step assumed polynomial, which is d of x times the q tilde of x plus the r tilde of x. Okay, so now let's go ahead and bring all this stuff together. Okay, so I'm coming from all of these guys, going to come down here, and let's wrap this up here. So I have d x times q tilde x plus r tilde x on the left. On the right, I get a p of x, which is what I'm interested in, minus a k plus 1 over b sub d times x to the k plus 1 minus d times the divisor polynomial. let's go ahead and solve for the one that I'm interested in. Okay, so that's the p of x polynomial. So solving for that, this means that p of x is equal to d of x. Okay, in fact, I've got a d of x here, and when I bring this term, all of this, to the other side, I've got a d of x right here, so I can factor that out, right? And if I do that, I can write this as the following: the q tilde of x, which is this term, plus, now we took this, the one that I've circled here, we've taken this to the other side, so the minus became a plus. I get plus a sub k plus 1 over b sub d x to the k plus 1 minus d, okay, plus the r tilde of x, which is that. Okay? Well, now I think you're beginning to see what we're doing here. I can now, since I'm trying to talk about existence of a q and an r, I can just call this entire bracketed term the q that I'm interested in, and I can just call this the r that I'm interested in. Okay? And so therefore, we have p of x is equal to d of x, which is, that's the p of x, this is the d of x, times the q of x, which is that one, plus the r of x, which is that one. And it's important that we note here that where the degree of the r, okay, the degree of the r, the degree of the r tilde polynomial is equal to the degree of the r polynomial, the remainder, which is just what we were calling r. And since this r tilde, this guy, happened at the kth level, that means that, in fact, that was at the inductive step, this has to be less than the degree of the divisor by the definition of the theorem. Okay? Because remember that this remainder, the r tilde degree, happened at the kth step. Okay? And so when we assumed the kth case to hold by the inductive step, let me write here of inductive step, that was assuming that the degree of the r tilde was it was abiding by the stipulation of what the inductive step, saying that in fact it had to be less than d. And so that completes the existence part. So let me say, hence, the existence part of theorem has been shown. Okay, so that leaves us with the uniqueness part. Okay, so let's do that, and then once we have the existence and the uniqueness, we've completed our proof fully. So here is the uniqueness part of the theorem. So to do the uniqueness part, we suppose that the polynomial can be written in the following ways. I could say that this is d of x times, let me call this q1 of x plus r1 of x And let me say that all of this is equal to d of x times q2 of x plus r2. Excuse me. Let's go up and see where we lost ourselves here. Okay, so let me go ahead and write this down below here, okay? So this is equal to d of x times q2 of x plus r2 of x. And what we want to show here, let me just call this my star 1 equation. What we want to show here is that q1 is equal to q2 and r1 is equal to r2. Okay? Or another way to write the star 1 equation is to bring the common d terms together. So I would have d of x times q1 of x minus q2 of x is equal to r1 of x minus r2 of x. Okay? Or actually, I got this backwards. This really should be r2 minus r1, I guess. Right? Or, and let me call that my star 2 equation. Or I could bring all of those back together. I could say that d of x times q1 of x minus q2 of x. If I bring these guys over, I get plus an r1 of x minus an r2 of x is equal to 0. Let me call that the star 3 equation. So here I have three different ways of writing basically the same thing. We need to show that q1 is equal to q2, okay? Just to abide by the same ways that I've been writing everything, let me say that q1 of x is equal to q2 of x and r1 of x is equal to r2 of x. If I can show that, then I've shown that, in fact, we have a unique q and an r, because they're, even when I started off with different q's and r's, calling them q1 and r1 and q2 and r2, at the end, if I show these two things to hold, that q1 equals q2 and r1 equals r2, then in fact, the q and the r are in fact unique. So we once again have two cases to look at. All right, so let's look at each one by one. As we did before, I have a case 1, i.e. d is 0. That means that the degree of the divisor is 0. Since the degree of the divisor is 0, I can say that the remainder polynomial has to be 0 as per assertion of theorem. Let's remind ourselves what the theorem was asserting. The theorem was asserting that when the degree of the polynomial is 0, then the remainder has to be 0. The remainder polynomial has to be 0. Okay, so if the remainder polynomial is 0, this implies then that so r1 of x is 0, and in fact r2 of x is 0, and this implies that r1 of x is equal to r2 of x, and they're both equal to 0. But since r1 is equal to r2, this implies that if I were to go into star 3 equation, by star 3, that I get d of x times q1 of x minus q2 of x plus r1 of x minus r2 of x is equal to 0. Okay? This means that this is 0, this is 0. This implies then that d of x times q1 of x minus q2 of x is 0. But what did we say by the theorem? But the divisor is different from 0 by definition. Let's remind ourselves of that, right? We're saying that the divisor is different from 0 by definition. This implies then that to make this statement true, that the q1 of x minus the q2 of x has to be 0. And this means if I take the q2 to the other side, I get that q1 of x equals q2 of x. And so that completes that part because we have q1 of x equals q2 of x, and I also have that r1 of x is equal to r2 of x. And so in fact what I was trying to achieve from the beginning I've shown. Okay, so q1 of x is equal to q2 of x, r1 of x is equal to r2 of x. Uniqueness in case 1 has been shown. I have one case left to do. Let's do the second case. Case 2, i.e. the degree of the divisor polynomial is greater than or equal to 1. And here we will do a proof by contradiction. Okay, so let's look at that by supposing that the q1 of x minus the q2 of x is different from 0. Okay, so I'm going to try and bring about some contradiction. All I need is one contradiction, and so long as I achieve one contradiction, then I know that this supposition that q1x minus q2 of x different from 0 is incorrect. That means that the opposite of this statement must be true. That is to say that q1 of x minus q2 of x has to be 0, provided I come up with any contradiction. All right, so well, if this supposition is true, then that means that the degree of this difference times the divisor polynomial, that means that this has to be larger than the degree of just the divisor polynomial, which happens to be, we were denoting it always as little d. Okay, however, but since the degree of the R1 polynomial is equal to, let me call that little r sub 1, is less than d, okay, and this is just by definition, and the degree of cap R2 polynomial, which I can denote as little r sub 2, is less than d. Okay, this is by definition. Here it is. All right, we're in that case. So when that happens, then that means that the degree of the R1 minus the R2 has to be strictly less than d. All right. Then we have a contradiction by star 2. That gives us a contradiction. Let's remind ourselves what star 2 says. Star 2 is the following relationship. We have this here in star 2. Okay, so if the degree of the right-hand side, let me just write that here so we see it. Okay, star 2 said the following. It said that we have basically q1 of x minus q2 of x times the divisor polynomial is equal to r2 of x minus r1 of x. Okay, so I'm having a contradiction here because since, so the contradiction part follows here, since this would mean that the degree of the left-hand side, let me abbreviate this way, has to be greater than the degree of the right-hand side, which can't be. Okay, we're saying that this is an equality by star 2, and so the degree of the left-hand side should be equal to the degree of the right-hand side. Therefore, we have the contradiction that we needed. Therefore, our supposition was incorrect. And because that's incorrect, that means that then, therefore, that in fact q1 of x minus q2 of x is in fact 0, which means that q1 of x is equal to q2 of x. Okay, and this implies then that the left-hand side is 0 of star 2 up above. This implies, therefore, that the right-hand side is 0 of star 2, which said what? Which says that R2, that means i.e. R2 of x minus R1 of x is 0. That means that R1 of x equals R2 of x. And so we've shown what we set out to show, that in fact there is uniqueness throughout. So thanks for bearing with this long proof, but it does show a complete treatment of this very nice and useful division theorem, or division algorithm as it's popularly called. And we learned that back in grade school, but here is a very sleek treatment for the polynomial field of polynomials through both an existence and a uniqueness treatment of that. And let's just remind ourselves real quick that we used the principle of mathematical induction throughout this process, and we also, in this step in particular, we used a proof by contradiction. So we illustrated two very important proofing techniques of mathematics. Thanks for watching, and hope to see you in a future video again. And by the way, Merry Christmas!